quite helpful because he didn't come to Storybook for about 25, 30 years, and he arrives and we make him work like a dog. So I'm very grateful that he's willing to use
I
this.
don't know what dog you have. My dog never did a day's work.
Anyway, finally he's going to give a lecture for the experts. So please.
Thank you. So I can tell you can hear me because I can hear me. So thank you, Louis, both for your hospitality and for making this place such an amazing place. It works for me. It's great. I also would like to thank Evita Nestoridi for her help in bringing me here and for hospitality. Thank you, Evita. Today I'm going to talk about well, something, but I'm going to have to learn how this thing works. I didn't take lessons. How do I make it go forward? Do I go, well, you... Good. Just good. This is joint work with two colleagues, Sourav Chatterjee and Laurent Miclo, and it's a, well, I don't know. I see that there's a program here on random geometry, and if you like, this is a part of that program. You'll see. Okay. Surely everyone here knows what a graph is, the usual combinatorialist graph with endpoints and some edges between them. Here's a question I'm going to start with. So there are, how many graphs are there on endpoints? There's 2 to the n choose 2 graphs on endpoints. Well, that's how many graphs there are. And so it makes sense, it's a finite set, it makes sense to pick a graph at random, look at a typical graph, and another way of saying it is, for each pair of edges, for each pair of vertices, there's an edge between them, and flip a fair coin, and if it comes up heads, put that edge in, otherwise don't. So that, pick a graph at random, okay? And I'm going to call it gamma 1, there it is. And now do it again. So pick another one at random. What's the chance that they're isomorphic? So 2 graphs are isomorphic if there's a 1-to-1 onto map from the vertex set of this graph to the vertex set of this graph, which takes edges to edges. Okay, so what's the chance that 2 randomly chosen graphs are isomorphic? That's a question. And well, it's small. I mean, it's small. How small? I mean, that's not so easy to think about. But whatever graph this is, there are 2 to the n choose 2 graphs that this one could be, and there are only n factorial permutations, right? So the answer is, the chance that they're isomorphic is less than n factorial over 2 to the n choose 2. And in case you forgot, that's small. So if n is 100, that's 10 to the minus 1300. It's small. Yeah.
You're assuming all your graphs, they don't have double edges? Or...
No, it's simple graphs, right? Thank you. Right. Simple graphs, no loops or multiple edges, right? And no directions, just, right. So, okay, so you got that?
You have to divide by the symmetries of one graph?
No. That's a bound. No. So, okay, that's for finite n is 100. So now let's let n be infinity. So makes perfect sense to pick a graph on infinitely many points. Just flip a fair coin for each pair of edges. That's fine. And that generates a random graph. And then do it again. So I now have 2 graphs on infinitely many vertices. What's the chance that they're isomorphic? And some people find it surprising, I still do, that the chance is 1, for sure, that they're isomorphic. So if you haven't seen that before, let's talk about that for a second. So here's a property that an infinite graph might or might not have, and I'm going to call it property star. I'm getting better at using this thing. So here's a property that a single graph might or might not have. For every integer n and m, and enumerate the points, for any x1 up to xn and y1 up to ym, distinct sets of vertices. There's another vertex z which is connected to all of the x's, and I didn't want to do that, I don't think. There's another vertex z which is connected to all the x's and not connected to any of the y's, right? That's a property that a graph could or could not have. And if you think about it, so fact one, a random graph, I'm calling it g infinity a half, has that property almost surely. And why is that? Easy to see. What's the chance it fails? Well, n and m are now fixed, and x1 up to xm are now fixed. At the moment, fix those, and so the chance that it fails is that all of the other vertices have to misbehave and not, the chance that a vertex succeeds is 1 over 2 to the n plus m. So the chance that it fails for everything is 1 minus 1 over 2 to the n plus m to the infinity, and that's 0. Take a limit, and then take the union over countably many possible sets of x1 up to xm. So that still gives probability 0. So random graphs almost surely have this property star. Okay. And now, fact two, if two graphs, random or not, both satisfy property star, then they're isomorphic. And the proof is easy, but let's go through it. I'm going to use a back and forth argument. So enumerate the first graph is x1 up to x2, x1, x2 up to x infinity. The second graph, y1, y2 up to y infinity. And suppose that I've constructed, so now these are graphs, they have some edges and they have some non-edges. Suppose I've constructed, suppose fm is my map that I've constructed so that it's an isometry that is onto its range. That is, I've constructed a graph from x1 up to xn into the second graph, which sends edges to edges. Okay, so now, if n is even, let k be the smallest index of a point which hasn't been assigned, right? Not in the domain of fn. I want to extend it to 1 point further. I'm going to extend fn to this new to one point further, and all you have to do is let u be. This graph is fixed. Xn plus 1 is connected to some vertices, u, and not connected to others. And so you can, because gamma 2, a potential image of xn plus 1 must be a neighbor of each of the images of the xi's, and not a neighbor of each of the points vj. And because gamma 2 satisfies property star, there are lots of points over here which you can match xn plus 1 to, and have that be now an isomorphism at stage n plus 1. And then if I want the map to be onto, so work backward, let k be the smallest index where yk is not in the image of fn. And then I can extend fn to fn plus 1 using the fact that property star holds in gamma 1. So okay, that's a little quick, but I think you certainly get the idea. So all graphs, almost all graphs, are isomorphic, so there's only one of them, right? So that has a name. It's called the Ratto graph, after Richard Ratto. But quite a few people discovered it independently. Logicians discovered it. After all, a graph is just you have a countable set, and you have with one relation, one symmetric relation. So graphs are natural things for logicians, and they discovered this, and many other people have. So Erdős and Renyi, when they heard about it, they said, therefore, infinite graph theory is uninteresting because there's only one of them. Okay, well, let's see. Well, here are some properties of the Rado graph. It's robust. That is, suppose I have the random graph, and I just knock out a few hundred vertices, just erase them, and knock out a few thousand edges, just erase them. That's another graph, right? Still has infinitely many vertices and infinitely many edges. And they're isomorphic because they both still satisfy property star. So it's robust in that sense. This is a characterizing property. If you divide the vertex set into k boxes any way you like, and then each set of vertices, there's an induced graph spanned by those. One of those graphs has to be isomorphic to R. It's the universal, that is, the Rado graph, any finite or countable graph embeds as an induced subgraph of the Rado graph. So it contains all graphs as induced subgraphs. It has a very nice, useful homogeneity property. Given an isometry that started, that is, you have a mapping from the graph to itself, which sends, just one-to-one and onto its range, and which sends edges to edges, there's an extension. It has diameter 2. Of course it has diameter 2, because if you have any two vertices, you can find some vertex which is connected to both of them, and that's an edge, and then there's an edge from here to here. So it has diameter 2. It's the limit in a logician's sense, Frese limit, of the set of all finite graphs. And for logicians, I've been told that that the set of graphs is just about as interesting as the rational numbers. Well, that's why you're mathematicians and not logicians, but the logicians do talk that way. It's a basic object in various points of view. So I'd like to understand it and for a minute and think about it. There are many other constructions of the random graph. Rado's original construction is deterministic, has nothing to do with random. Take these integers, 0, 1, etc. And here's a rule: connect vertex I to vertex j if and only if the ith bit of j is a 1 in binary. Okay, so let's think about that for a second. So 0 is connected to all the odd numbers, right? The first bit of 0 is 0, and all the odd numbers begin with 1, right? So the 0th bit of, the 0th bit is the first bit going from the left. So 0 is connected to all the odd numbers. 1 is connected to the j's, which are 2 or 3 mod 4, and 0, okay, and so forth. So what you can see, and this easily satisfies the property star, and so this is a non-random, if you prefer that, construction of the Rado graph. And I won't check that more because it's not what I really want to talk about. But but what to think about is, vertices have infinite degree, right? Right. Every vertex is connected to half the points. It's not locally finite or anything like that. Here's a number theoretic construction, if you like things like that. Let V be the set of all primes which are 1 mod 4. Connect 2 primes, P and Q, if one is quadratic residue, if P is a quadratic residue mod Q. And that's the Rado graph. That's the random graph, and that's easy to check also. And there are about a dozen other constructions. Yeah, right. And there are about a dozen other constructions, and the best I'm going to do there is to tell you a wonderful article. If you get nothing out of this talk except looking at this paper, my friend Peter Cameron wrote an article called The Random Graph, and that chronicles lots and lots of features. I wrote this one down. It satisfies the 0-1 law. any first order property holds in the Rado graph if and only if it holds in almost all finite graphs with high probability, with probability tending to 1. Now this is an error. What are some first order properties? They sound great until you actually think about some natural properties of graphs and say, is that first order? Most interesting properties of graphs aren't first order. In particular, I was wrong. Connected isn't a first order property. Diameter 2 is. Property star is not Hamiltonian, circuit, chromatic number. But meanwhile, it's an interesting, that's another sense in which it captures all finite graphs. That's enough, okay? So I've introduced you to the Rado graph. That's where we are now. So I'd like to understand it in my own way, and I'm a probabilist, and my way of understanding things is to do random walks on them. And another way of saying that, if you're an analyst, you know, we understand the geometry of manifolds by understanding the behavior of the Laplacian on them, and the eigenvalues and eigenfunctions of Laplacian tell you a lot about geometry. And so I want to make a kind of Laplacian on the Rado graph and think about it. And of course, it's not so easy to do simple random walk. It doesn't make sense if you're at a vertex to pick a neighbor at random. Sorry, there's infinitely many. We don't know how to do that. Well, let's do this. Here's a way to get started. Suppose you fix a probability distribution. I'm calling it Q here, Q of V, okay? And it just sums, you know, the probability distribution on a countable set. And I'm now going to define a transition kernel. And just, it's written down there, but let me just tell you what it says. I'm at V, okay? And I want to pick where to go in the next step of a random walk. Well, look at all my neighbors. There are countably many of them. Tough, okay? And restrict your probability. Sorry, Dennis, don't heckle me, please. I mean, it's a graph. One away.
What does it mean, a neighbor?
If there's an edge. 2 points are neighbors if there's an edge. Sorry. Excuse me. Okay, that wasn't heckling. That's trying to understand. You're capable of both. Thank you. So you're at a vertex V. Look at your neighbors, things that are one away, and restrict your probability to those vertices that are one away, and then pick one of those with probability proportional to the weight, Q of V. Okay, so I wrote that down I wrote it down in, let's go forward. There we are. I wrote that down. So the chance, this is an infinite matrix. The chance of going from V to V prime in one step is proportional to this weight I'm choosing Q of V, and then this is a normalizing constant. So that gives you a way of marching around on the vertices. And so this is an infinite matrix, and it operates on L2 of the vertex set, but let's say that for a second. So here's a very easy to check fact. This operator is self-adjoint with respect to this measure on the vertices. So pi of V is a probability distribution on the integers, and it's proportional to Q of V, my weight, times Q of the neighborhood of V, and then there's a normalizing constant. And so that is a probability distribution. And so you look at L2 of the integers with this measure on it. K is a linear mapping of the vertices into self, so it sends functions into functions, and this mapping is self-adjoint. That's what reversible means, but you can just check it this way. This is the normalizing constant, and the proof is just look at this product, pi of V times K of V, V prime. Well, just by definition, pi of V, I told you what it was. K of V, V prime is this ratio, and these guys cancel out. And what's here is symmetric in V and V prime, so it's equal to pi of V prime, K of V prime, and that's enough to prove self-adjointness. So this operator has real spectrum, and if you walk around, the fundamental theorem of Markov chain theory says if you walk around, start any place and walk around according to this K, and if I ask where are you after a long time, the chance that you're at V after many steps is proportional to the stationary distribution. This is a left eigenvector with eigenvalue 1 of this matrix. So with Evita and several other people in the room, we study how many times do you have to shuffle a deck of cards to mix it up. Well, how long do you have to run this random walk until it's close to stationarity? That's a kind of first order type of question. But first of all, I said that KL of V is, if you start at V and you go L steps, what's the chance of being any place? That converges to pi as L goes to infinity, and what's the rate of convergence? And it's a complicated graph. It's not so easy to understand. First of all, it's sort of random, but it seems as if it should converge fast. R is connected. It has diameter 2. Every vertex is connected to half of the others. Well, how fast will it converge? That's not so easy to think about. Could be that 2 steps is enough, or 5 steps is enough, or 10 steps is enough. Some bounded number of steps could be enough. That's not the right intuition, so let's not leave you with that thought. In order to talk about it, I'm going to work in this thing I'm calling the Rado Boolean model. That is, I is connected to J if and only if the ith bit of J is a 1. That's the deterministic version of the Rado graph. And I'm going to work, I didn't say what my probability distribution was, but let me pick one just for the moment, and I'll talk about what happens if you change it. But let Q of J be the usual geometric distribution, 1 over 2 to the J plus 1 for J equals 0, 1, 2. So flip a fair coin until the first head. What's the chance that you have J tails before the first head? But anyway, this is a probability distribution on the integers. And just to be a little bit honorable, this measure, the measure we define, pi of 0 is 1/3 times 2/3 if you parse it divided by z, and pi of 0 is less than 1, and that lets you say that z is bounded between 1 and 6. So the normalizing constant I'm working with is between 1 and 6. And now, okay, here comes infinity, but in its own funny way. This is a notation I'll use. 2 to the brackets k plus 1 is 2 to the 2 to the 2 to the 2 k times. Okay, that's familiar in certain parts of the world. If you listen to Tau and Gowers and towers of 2, Ramsey theory. Anyway, that's the notation. For example, these numbers grow very rapidly. 2 to the 0 is 1, 2 to the bracket 1 is 4, 2 to the bracket 2 is 16, 2 to the bracket 3 is 256, and they grow pretty fast. So I'm going to start the Markov chain at 2 to the k. So, sort of far away, but I don't know. I'm allowed to, I'm doing math, I'm allowed to say the only vertices which are smaller with the usual ordering on the integers connected to J is 2 to the k minus 1. Okay, that's easy to check, and it's a claim. The higher vertices that are connected to 2 to the k have extremely small, k-fold infinity iterated 2 to the k small probability. So what does the walk do? Well, the walk, picks one of its nearest neighbors with probability proportional to q And so what the walk will do with high probability, but very high probability, and you have to keep careful track of it, it'll go from 2 to the k, it'll go down by 1, and then down by 1, and then, you know, it'll just do that. And eventually it'll get close to 0, and then it'll bobble around 0. And this argument, if you do it a little bit more carefully, says that the chance that the walk started at this iterated 2 to the k tuple, the chance that the walk, I'm calling the walk n steps, calling the walk xn, is equal to 2 to the k minus L, is, for any L is allowed to vary, where is it likely to be, is less than, you know, 1 over 2 to the k minus L for every n. And that says, that allows you to get a lower bound. That is, this norm is the total variation distance between measures. The distance between two measures is the sup over all subsets of P of A minus Q of A. So take the sup over all A, and that's the norm on measures. I'm using the usual total variation distance, and so if you start this funny walk at you know, this 2 to the k away, the chance that you're, you know, in stationarity is bounded away from 0 as long as L is L is not too big, and so that gives you a lower bound on mixing, and let's say what it is. Corollary, it takes log to the base 2 star of I steps, and I don't know if people know that notation, but you know, there's log, there's log log, there's log log log. Keep going, right? And how many times do you have to go until you get something less than 1, or, you know, less than, and that's log star. Right? Yeah.
To use this distribution on the integers to talk about random walks on the Rado graph, do you have to like choose an ordering of the edges around each vertex?
Well, it's a countable set, and I'm saying it's almost an algorithmic question. It's a countable set, namely the neighborhood of a given vertex is some countable set. I have a measure on it. You know, I have a probability measure on it because I normalize it. When I say pick, I pick one of the neighbors with probability proportional to Q, restricted to that set. You know, you can choose from a measure on the countable. Sure, you can order them if you like. Right? But I'm just, you know, just picking from a measure on a countable set. I'm assuming, you know, you have to. If you actually want to do it, you have to write it down and order them. Sure. Right? But you can order them, you know, in size order. That's okay. You know, they're integers. It's okay. That part's okay. So what we just proved is that it takes log star steps to converge starting from I, at least for infinitely many I. And just to remind you, if I is contained in this interval, 65,536 to 2 to the 65,000, log star of I is 5. So it's very, very slow, but it's bigger. You know, it is going to infinity. I mean, it does depend on where you start. And the main theorem that we had to prove, that we proved, is that that's the right answer in the following sense. There are constants that A and B, which are real constants, 2 and 6 are not astronomical constants, they're real constants, such that if you start the walk at any I, for all I, and you go L steps, how close are you to stationarity? Well, it's less than or equal to A times this log to the base 2 star of I times e to the minus b of L, where L is the number of steps. So as soon as L is a little bit bigger than log star, this will be small and tend to 0. So this says that order, I haven't gotten the constants right, and I don't know whether there's anything like a cutoff, but this says that order log star steps suffice in order to get to randomness. So So I have been doing random walk a very long time, and you know how many times do you have to shuffle cards? Well, it's log n log n. I mean, I never saw anything like log star come up as a rate of anything. I said it to my friend Jan Vandrek. I said, gee, I had log star, and he says, well, it's not inverse Ackermann. So, okay, not everybody can be happy, but it's very, very slow. But it is going to infinity. And the proof of this argument needs us to, which is why I was doing it. Remember, I'm hoping to learn some things about the Rado graph in asking these questions. The proof uses a curious geometrical property of the Rado graph. So fix a model of the Rado graph, whichever one you're happy to work with, and I is a vertex in the Rado graph, and it has neighbors, a countable collection of neighbors, and those neighbors are integers, labeled by integers, and look at the minimum value of all the integers. It's a countable set. I'm now working in the Erdős-Rényi model of the Rado graph. But so this would then be a random quantity. So look at the minimum value of a neighbor of I. Okay, and here's a math statement. Let B be the event. That event meaning in this probability space. Let B be the event that for all x in the neighborhood of I, the neighbor of the minimum value of the neighbor of x is less than I. Okay, so that takes a little bit of looking at, but I hope not too much to look at. So that for B is the event that for all x in a neighborhood of I, that rho of x is less than I, and that should hold all the time. And then it's funny that you can write a formula for that, but you can. And the probability of B is bigger than a quarter. It's equal to this, but it's actually, so it's bigger than a quarter. It's bounded away from 0. So that's a property of the geometry of the Rado graph, and a way to translate that into something useful and interesting is this. Consider, I've defined this row of x, and for x contained in n of I, consider the edges x row of x for x contained in n of I. And the claim is that, it's not so hard to see, that the graph in which the vertices are n and the edges are this f, or this set f, is a tree. Okay, so it's a tree. It's connected. It's a tree on the integers. What we do is do our analysis on this tree and show that the operator has a spectral gap in L2. The key technique there is something that I keep thinking it's a classical part of hard analysis, but it seems to have disappeared. I ask our analysts, well, I used Hardy's inequality, and they say, which one is that? And so, sorry, I don't expect you to know it either. But Hardy's inequality, I thought I would have a blackboard, and I could have one, but let me I'll just tell it to you in the air. Suppose AN is a sequence of non-negative numbers, A1, A2, up to A infinity, and look at the average of the first k AIs, okay? So 1 over k, summation AI, and that's a number. Take the square of that number, and then sum that over k. So look at the average of the first k things, and then sum those averages over k, sum of the squares over k. That's less than or equal to 4 times the sum of AI squared. Okay, and or if you like, if that helps you, the linear map of sequences that takes a sequence of numbers into their partial averages, their Cesaro averages, sends L2 into L2. That's another way of saying it, if you like, and the constant is 4. So that's Hardy's inequality on the line in one dimension. This Hardy's inequality with more general measures. And the classical development of Hardy's inequality allowed you to replace the uniform distribution with 2 measures, and then if you have 2 general measures, and then you have to argue hard and work hard, and it's a subject that has books about it, to get the right analog of 4. But what's a constant as a function of the 2 measures? But that's the subject of Hardy's inequality. But Hardy's inequality is very, very useful for one-dimensional problems. And it stinks for 2-dimensional problems. It just doesn't work well, and it really, but a tree is sort of one-dimensional. A tree is sort of one-dimensional. And there is, we're partially responsible for it, there's a notion, a useful notion of, with explicit constants, of Hardy's inequalities for general trees. And that's what we needed to do. So what we do is use this geometric property of the Rado graph, and then some analysis, and it's, you know, it's many pages of analysis, but we have this tree embedded, and we can just use the fact that a tree is sort of one-dimensional, and we were able to prove that this operator had a spectral gap, that the second eigenvalue of the Laplacian associated to this Kij is bounded away from, well, for probabilists, the spectral gap, the first eigenvalue is 1 and they go down, and for analysts the first eigenvalue is 0 and they go up. But I mean, it's the second eigenvalue is bounded away from 0, you know, by a constant. We wrote down a real constant. So I won't say, I don't know that people want to see anybody's dirty laundry, and I wasn't planning to do it. What did I do in this talk? Well, the first thing I did is introduce the Rado graph, and if you haven't met that before, it has many cousins, and they're very interesting objects. It's sort of a topic in logic, but there's, you know, these are universal limits of natural categories, but the set of all graphs. But there's a universal metric space. There's a limit of this, and Gromov has used that, the limit of all metric spaces, and but many naturally defined objects have limiting objects, and this is the one for graphs. I tried to explain an example of the analysis using random geometry. That is, here, if you use the Erdős-Rényi model, this is a random geometry, and let me at least say it. You can make everything finite. That is, you know, instead of working with an infinite graph, I could work with a very, very big graph, and then there are finite versions of these theorems, and something like log star is still the right answer. I don't know that that helps anybody, but this is sort of cleaner, and the n that you have to work with is so large that it may as well be infinity anyway. And the last thing that I think that I found an example of an extremely rapidly converging Markov chain. Log to the base 2 star steps are necessary and sufficient, which I find curious and interesting. What remains to do? Well, there are lots of problems I can't do. In case you want to 2 examples. Well, my analysis, the lower bound didn't matter very much, but my analysis really did use the fact that I was working with this geometrically decreasing measure, Q of I. And of course, the question about rate of convergence of random walk makes sense for any measure on the integers, and we haven't done that. We did take one parameter family of measures, namely let the measure of I be 1 minus epsilon times epsilon to the I, where epsilon is a parameter. So, flip a coin with probability of heads epsilon, what's the chance that you have I heads before the first tail? And then as epsilon, of course, goes to 1, I guess, that gets flatter and flatter, but that's still very, very special. And I don't know about more general measures. It's natural to try to take 1 over j squared as a measure, something like that. A very interesting question, but we were able to analyze things on this giant thing by finding a kind of spine, by finding a tree that captured everything, and then we could do the analysis on the tree, and then what was left was didn't cause any trouble. And are trees always enough to show a spectral gap? That's a math problem. Suppose you take this random walk, but with a general Q, and is the restriction of the walk to a tree always enough? And in general, in doing analysis on infinite graphs, and there is some theory, and I'm not going to tell you about it, but there is some theory that suggests that trees are enough, and we can't prove that or don't. If you wanted to look, the paper is the 3 of us and a random walk on the Rado graph, and it appeared in a book dedicated to Harold Whittam, Toeplitz operators and random matrices, and it has all of the details that nobody wants to see except the authors, and I didn't put them in this slide. But this is an example of rates of convergence and the kind of thing I do, and I'm glad I had a chance to tell you about it. That's it.
Thank you very much.
Is the Rado graph have finite degree at every vertex?
No, countable at every vertex. Right? It's just not locally finite, but still you can do. That's why I did what I did. I mean, that's right. It's countable. Every vertex is connected to half of the others, whatever that means. Right?
A question in the back.
So if you choose the probability that 2 vertices are connected by an edge to be any other number than 1/2, do you still get the same graph?
Yeah. Oh, yeah. Thank you. I should have said that. If you for every I and j, you flip a p coin, and then put an edge in with probability p, and not an edge with probability 1. It's isomorphic, right, for all p. It's there. I mean, it has amazing properties, and its cousins, these cousins are. They're interesting objects. And but thank you.
Yeah, I'm still fascinated by the very first statement about isomorphicity with probability 1.
Good.
So, does it mean that I have to take limit properly? Namely, for example, define some accuracy, so isomorphic after some finite number of vertices, and then in the limit I'll get 1. Is any way?
No. Well, I mean, could I make a finitistic quantitative version of what I just said is sort of another way of phrasing your question. So the way I'll come to, don't let me get away with anything, I don't want to. The way I made a finitistic version of it is suppose I have 2 Erdős-Rényi graphs on n vertices, okay, n and n, and then I flip a fair coin, so they're both 2 random graphs on n vertices. What's the size of the largest isomorphic, subgraph? I mean, that's a question. And we answered that. It's a separate paper. And it's around log n, and it's very, very fixed. It's log n plus, plus 1 or minus 1. Integer part of log n plus 1 or integer part of log n minus 1 or integer part of log n. So it's very, very fixed at around log n. And then when I said there's a version of these theorems, the log star limit theorems for finite graphs, we use things like that. But you know, that's a wimpy little thing. It's only log n big, but if n goes to infinity, log n goes to infinity too. So that helps quantify, I think, what you were asking about. I don't know if it captures, and probably, you know, it's just it's more things to think about.
Yeah, Peter?
And so I want to understand what you mean that the tree captures the spectral gap. Are you creating a new matrix where, you know, when you're not on the tree, you put a zero entry, you force the walk to stay?
Yes. So just make there's this tree, and I've got my weights on the vertices, which are the Q weights, say, and then just make that random walk.
So if you exit the tree, you don't do that.
You don't. I can't. I'm going to restrict the random walk to the tree, and then you know, by Dirichlet forms, by standard analysis, if you have a you know, property of whatever it's called, but if you have a property for a smaller thing, that gives you information about the spectral gap of the bigger thing. So getting a bound on the spectral gap of the walk restricted to the tree gives you a bound on the, let me say one sentence as long as at least, so ordinarily the spectral gap isn't enough to give you mixing. You need the bound on the mixing rate needs the measure at the starting state times the spectral gap to the nth power. So what we do is we know that this walk, wherever it starts, is driven back toward the origin. So if I go log star steps, it's close to the origin. So I can forget about the stationary distribution. That was an important step. But there is a theorem of Lindenstrauss and another Israeli functional analyst, which gives hope that restricting attention to trees is enough for certain questions in analysis on infinite graphs. And it's interesting, and we didn't do it. So but if anybody's interested in things like that, take a look.
Is there also an infinite random tree, or does that not make sense?
Yes, there's an infinite random tree, right? There's an infinite random tree. I mean, yes. I don't, it's not my part of the world, but I do remember that there's an infinite random tree, and there's an infinite random k-regular graph, and there's an infinite random a lot of things. This notion of a Frese limit, the logicians call it, given any model, and then you can have finite sections of it, and then there's a limiting object of it, and it's very, very general. And so there is a notion. It's not my friend, so I can't describe it to you.
So do you think your tree is that tree, or is it a different?
I doubt it, but might be because they're kind of universal. I don't know. That's a good question. I hear a good question. It's a good question. I don't know. Our tree was sort of forced on us, and it's pretty natural. We had several different ways of getting our hands on it, and they all pointed to the same tree. But I don't. Good question. Thank you.
Is it a maximal tree?
It's not a maximal tree.
No. Is there a maximal?
Is there a maximal? I don't know, Dennis. I don't know. That's a good, because that would be a natural thing to work with. But would there be a maximal tree? From maybe a lot of them. But of course, then I could choose a maximal tree. Right. Yeah, no, the question makes perfect sense. I don't know the answer to it.
So you were mentioning earlier that there's a link, there's a kind of geometric perspective on these things. And a lot of the words you use towards the end, they also appear in
analysis.
In geometry as well. So this spectral gap, is it about solving the graph Laplace equation? Yeah,
so spectral gap just means, so I have my operator Kij, right? And the Laplacian is the identity minus Kij.
So it's the same.
Yeah, and so that's why for analysts and for me, for analysts, you know, the smallest eigenvalue is 0, and and then they go up. And for probabilists without the 1 minus k, the biggest eigenvalue is 1, and then they go down. So we always take some translating. And the spectral gap is, there's a Dirichlet form, there's an energy form, and summation of f of x minus f of y times pi x times kxy. I mean, and it's the same. This is the same.
When you study harmonic forms on manifolds, the key inequality is this, I guess.
Poincare inequality. Which? Weissenbach.
So is this Hardy inequality that or weaker than that?
I don't know. The Hardy inequality is very close to a Poincare inequality.
And then it's the same.
Thank you. Now I can say, oh, I heard it was the same. I was at Simon's. But I didn't know that. Right. It is a Poincare inequality, right? This is Hardy inequality. The constants that you get out of Hardy's version of it are better if you care about constants, and they can be important. Thank you.
Okay, as we say in Spanish, brief and good, that is good. Thank you very much.